All right, I thought I'd shoot another video here. Microphone closer. On working out some more of these examples of the problems from lesson 4. Ones that I hadn't assigned to the various groups, so hopefully you get the gist of how these things work. So this problem number 7 says you're planning on making an open rectangular box from an 8 by 15 inch piece of cardboard by cutting congruent squares from the corners and folding up the sides. What are the dimensions of the box of largest volume you can make this with? Okay, so we will start with the picture. I guess we also follow our pattern from before. It says what are the dimensions of the box with the largest volume. So we're trying to maximize volume. Which means that we're going to need an equation for volume. We've got this piece of cardboard that is 8 by 15. We're going to cut corners or squares out of the corners of this thing. So these will be gone. And then we'll fold up the sides into a box. Okay. Which means that this length of the box now, if we call these corners x by x, since they are squares, then this is going to be 15 minus 2x in there, and this is going to be 8 minus 2x there. So we should be able to say that means the volume of my box is going to be 15 minus 2x long, 8 minus 2x wide, and x deep. I want to maximize this volume, which means I need the derivative of this. That might be easier if I had this multiplied out into just a single polynomial. So let's see, I got a 120 and a minus 46x plus 4x squared, all times x. So that's a 120x minus 46x squared plus 4x cubed. That's the equation for my volume in terms of x. So to find maximums on this is a cubic function. I've got to imagine an image of what this looks like. It's positive cubic, so I know it's doing something like this. So it's likely this kind of point that I'm looking for. But I'll find out by taking the derivative and setting it equal to 0. So the derivative is 120 minus 92x plus 12x squared. Setting that equal to 0 and solving. Let me see if how much I can factor out of there. Looks like probably just a 4 maybe. Yeah, I can pull 4 out. So I'll divide everything by 4 as I set it equal to 0. That'll leave me a 30 minus 23x plus 3x cubed. I'm not sure if this is going to, I could try to factor this. 13 and 10 sounds 33. I'll just go to the quadratic formula. Okay, so my quadratic formula is going to say x is equal to the opposite of b plus or minus the square root of b squared minus 4 times 30 times 3 all over 2a, which is going to be a 6. So I have a 23 plus or minus the square root of 529 minus 360 there, all over 6. And that does work out. That's going to be 23 plus or minus 13 over 6. So 23 plus 13 is 36 divided by 6, or 23 minus 13 is 10 divided by 6. So that gives me a 5/3 or a 6. Okay. I would suspect that the maximum is going to be 6. However, if I try to put a 6 in for x in this problem, what I'm noticing, let me do a second derivative real quick so we can test this. That's going to be a negative 92 plus 24x. If I put a 6 in for the x here, I'm going to get a positive number, which means I was concave up. So the 6 is definitely going to be a minimum. And I see some issues with the 6 anyway, because, for example, if I tried to put it in here, I would get a negative dimension on that box, which doesn't make any sense. So 5/3 must be my best answer. Okay, 3 times 13 times 6. Okay, so I'm going to do 5/3 of an inch out of each corner. If I don't want to know what its volume is, then I'm just going to plug the 5/3 back into the volume equation to come up with what that is, but that's just putting numbers in now. So I'm going to use video time for that. I could demonstrate over here that multiplying this by 5/3, so divide the 24 by 8 or by 3, and I get an 8 times 5 is a 40. Negative 92 plus 40 is definitely still a negative number, so concave down at that point, and so it must be a maximum value. Let's try another one. Designing a can. This time a can instead of a box. This says, what are the dimensions of the lightest open-top right circular cylindrical can that will hold a volume of 1,000 cubic centimeters? Lightest open top right cylinder, so I'm going to be minimizing the material that I'm using to build this, so that's a surface area. So I'm going to need an equation for a surface area. Let me draw my can here and get some dimensions on that. So there will be no top, okay? We're told the volume is going to be 1,000 cubic centimeters. So the dimensions normally I would need here are the radius of the base and the height. And so my surface area, I'm going to need the bottom, which is pi r squared, and then the middle to wrap around the side, which is a 2 pi r times h. Okay, look at that. I've got too many variables in there. I need it down to one variable. I haven't used the fact that the volume is 1,000 cubic centimeters yet, but the volume of a cylinder is the area of the base, pi r squared, times the height. That is equal to 1,000, so the easiest thing to solve that for is to say that the height is going to be 1,000 divided by pi r squared. So if I substitute that into my surface area equation, I'm going to get a pi r squared plus 2 times pi times r times 1,000 divided by pi r squared. I can simplify a little bit. These pi's will cancel. This r will cancel with that r. And so my equation now looks like pi r squared plus 2,000 over r. This is my surface area equation. It's the thing that I want to minimize, so I'm going to take the derivative of that and set it equal to 0. That's going to be a 2 pi r minus 2,000 over r squared. Set equal to 0, that's going to say 2 pi r has to equal 2,000 over r squared. If I multiply both sides by the r squared and divide by the 2 pi, that's right, yep, 2 pi r is 2,000 over r squared. So I'm going to get r cubed is equal to 1,000 over pi, which means that my radius that I'm looking for is going to be 10 over the square root of pi. So that's the radius. I could plug that in then to this equation to get the height. So r 10 over root pi, and the height is going to be 1,000 divided by pi times 10 over root pi squared. Those are going to cancel. I'm going to get 1,000 divided by 100, which is 10. So a height of 10 and a radius of 10 over root pi is what will be my lightest open top cylindrical can with a volume of 1,000 cubic centimeters. Let's try another one. Maximizing profit. Okay, the equations below represent the revenue and cost with X measured in thousands of units. Is there a production level that maximizes the profit? Well, it tells me right there, maximize profit. So I will need a profit equation. Profit is revenue minus cost. So that's an 8 root X minus X minus 1 cubed over 3 minus 1/3. Make it a plus 1/3. Once I do the derivative, that's going to kind of be irrelevant anyway. So the derivative of the profit is, that's x to the 1/2, so 4 over root x minus, this is going to be x minus 1 squared. When I do that derivative, the 1/3 is going to go away. I want to know when this thing is equal to 0. So where does 4 over root x equal x minus 1 squared? Probably to solve that and understanding that I'll have to look for extraneous roots, I will square both sides of this and get a 16 over x equals x minus 1 now to the 4th power. So it looks like I'm going to have an equation that looks like x times x minus 1 to the 4th power. I multiply that over there, minus 16 is equal to 0. Going to be some work definitely to do on that one. I think that's probably a large enough polynomial that I'm going to go to my graphing calculator and take a look at what the graph of that looks like. So x times x minus 1 to the 4th power minus 16. Let's take a look at what we are looking at here. I definitely have a 0 visible here. Use my calculator to figure out what that is. It's giving me a 0 at 2.578. And let's see, do I believe that that is if I did at 2.57, that's going to be a positive number minus that 1.57 squared. I'm looking to maximize profit, so I'd like this thing to be concave down. I'm going to do a first derivative check on this to see if I found the right one. So So if I go 4 divided by the square root of 2.578 minus 1.578 squared actually gives me, oh, I was putting that into the derivative, that's where I get the 0. I wanted to check something to the left of it and something to the right of it. I didn't do that very well, except that I rounded down, and to the left I got a positive number, and so to the right, if I put, I'll put something nice in here like a 4, so square root of 4 is 2, and I would get a 2 minus, and then 4 minus 1 is 3, squared is 9, so that's going to be negative to the right, and to the left, if I put a 1 in here, this is not what I wanted to do anyway, if I put a 1 in, I'm going to get 4, just 4, so it was increasing before, then I have my horizontal tangent, then it's decreasing, so that is a maximum, and so this is in its closest state here, 2,578 units. Since x was in thousands, and I want to produce 2,578 units of this thing to maximize my profit. Okay. Did it ask for anything else on there? Okay, is there a production level? That is the production level that I came up with. Okay, next problem. Tour service. I got 2 more problems that I'm going to do. You operate a tour service that offers following rates: $200 per person if 50 people go on the tour, and for each additional person up to a maximum of 80 people total. The rate per person is, I should say, reduced by $2. It costs $6,000 plus $32 per person to conduct the tour. How many people does it take to maximize your profit? Okay, so we want to, again, maximize profit. Profit is revenue minus cost. And in this case, we're talking about numbers of people. So the profit for in passengers is the revenue for in passengers minus the cost for in passengers. So let's see if we can come up with a revenue. We have normally $200 per person if 50 people go on the tour. If we, that rate, or the number of people, so if we have 50 people, if we have more than 50 people that go on it, so we'll do 50 plus n, and then that rate is normally $200 per person, but we'll take off $2 per person as long as the n is bigger than 50, and all the way up to 80, so it does create some endpoints on this. Okay, I think that is my revenue, because that is the cost times the number, so number of people, this is dollars per person, so this is my revenue. My cost is $6,000 in fixed costs plus $32 times all the people that I take on there, which is going to be 50 plus n. So a little bit of simplifying on these things. 5 times 2 is a 10 with 3 zeros. 200n minus 100n is 100n minus 2n squared. This is going to be 32 times 50 is 1600, or 100, yeah, 1600. 16 times 100. 1600 onto that is going to be 7600 plus 32n. And so my profit is the revenue minus the cost. So my 10,000 plus 100n minus 2n squared minus 7,600 plus 32n. Simplifying that, I'm going to have 10,000 minus 7,600 is 2,400. 100 minus 32 is 68. Minus 2n squared. So this is my simplified version of the profit. Okay. It is a quadratic that opens down, so there definitely is a maximum value. The derivative of the profit then is 68 minus 4n. If I set that equal to 0, I'm going to get 68 is equal to 4n. And n, 68 divided by 4, those are 117 times. So 17 additional passengers. How many people does it take to maximize your profit? We're going to need 67 passengers. Will maximize the profit. All right, I've got one more for you. The strength of the beam, I'm pretty sure, yep, okay. Strength of the beam, it says the strength S of a rectangular wooden beam is proportional to its width times the square of its depth. Okay, so we can read an equation out of there. I guess to begin with, find the dimensions of the strongest beam. Okay, so we want to maximize the strength of the beam. There's a picture in the book that goes along with this that I will draw here in just a second. So the strength S of a rectangular beam is proportional, we need a constant of proportionality, to the width times the square of the depth. Okay? So that's what that equation looks like. The constant of proportionality is there because the strength of the beam probably depends on what kind of wood you're cutting it out of. So they're giving us a cross-section of the log here, and we can cut this beam in a variety of different ways out of there. We have a 12-inch diameter cylindrical log, so this is 12 inches across there. This would be the width of the beam, and this is the depth of the beam. And I've got a little Pythagorean theorem staring me in the face there. So the depth squared plus the width squared, I can see, is going to be exactly equal to 144. This is the equation over here that I want to maximize. Too many variables. The k is not a variable. But I could solve this thing for d squared. It says d squared is 144 minus w squared. And I could solve that for d, but I've got a d squared waiting in this equation anyway. So let me rewrite my strength equation to be that constant of proportionality times the width times 144 minus w squared, which I can simplify to 144 times k times w minus k times w cubed. So this is the strength of the beam, and now just has one variable. I want to maximize the strength of the beam, so I'm going to take the derivative and set it equal to 0. This is going to be 144 times k minus 3k times w squared. When we set that equal to 0, we get 144k has to equal 3 times k times w squared. I guess it's a quadratic, so I should be able to get it from here. Divide everything to start with by 3k. And we get 48, the k over k is 1, so I get 48 equals w squared. So w is the square root of 48. 16 times 3, so that's 4 root 3. It wants to know what dimensions to cut out of that. So my w squared, I just figured out that this was 48. So 144 minus 48 says my d squared is going to be 96. So d will be the square root of 96, technically plus or minus, but the negative doesn't make any sense in this problem. And I believe that is, let's see, 96 get divided by 16, I'm fairly sure. Yeah, that's 6, so that's 4 root 6. Okay, or 4 root 6. So my width is going to be 4 root 3, and the depth is going to be 4 root 6. And we see the constant of proportionality ended up canceling out, which tells us that the proportions on the beam to make it the strongest are true regardless of what kind of wood this is made out of. But if we were actually calculating the strength, whatever units strength have in it, we would need the k value to get a strength number out of this thing. Okay. So there is a final example there. Hopefully you're tired of watching video by now, but we'll get that out to you along with a copy of these notes.